Welcome everybody to my talk. Hope you all had a nice break. So my name is Tiark Rompf. I'm a first-year assistant professor at Purdue University, and before I was working for Oracle Labs. And I'm going to talk about how types can turn a SQL interpreter into a SQL compiler. And I would like to start my talk. It's a bit garbled here. Let me fix this quickly. All right, I would like to start my talk with this famous quote by David Wheeler, which says that any problem in computer science can be solved by adding a level of indirection. And if we talk about databases, then database management systems are really a prime example and a success story how this works really well, right? So instead of implementing your own I/O and data processing, you can just ship a query to a database and have it run it, right? And it will work. But there's also another angle if you think about Joe Armstrong's keynote yesterday, that all these database systems are really complex. So if you look at commercial or open source database systems, then the code bases easily go into the tens of millions of lines of code. And this makes it a bit difficult nowadays because the circumstances are changing, right? So we have much more data in memory, and that fundamentally changes the constraints for how to optimize your system, for example, right? Because I/O is no longer the bottleneck, but these days compute is actually becoming much more important. So the question is, with these millions of lines of code base, is all this complexity really essential, or can we do something more simple? And what I would like to show in this talk is really just implementing a very small SQL processor in Scala in just under 500 lines of code, and actually getting good performance out of the system. So let's start with some coding. So I've prepared a little worksheet here, so I hope it, there we go. And I just have a small CSV file here, which I scraped from the web. So this is basically the program of the Future of Programming workshops. No, it's all the Strangeloop workshops, actually. So now I want to do some processing on this. Excuse me? Make the font size bigger? Yeah. That good, or more? Too much? Okay, seems like people can't agree. Well, let's just leave it like this, and I hope it's going to be fine. Right, so this is a CSV file. We have each line in the file is basically a record of data, and now we want to process it, right? So well, I can I'm gonna remove this line here, and I can create a new scanner object. I pass it the file name, which is in source data talks.csv. And I can do something like, well, first is in dot next until a end of line. And then I'm going to print this out. In the background, I have SBT running here. This should be a character, not a string. This recompiling in the background whenever I hit save, and there we go, we got the first line here. Right, and I can continue with that, so I can say while in has next, well, line is in next, and print out this line if I want to. Compiling. There we go. Right, so now I want to do some actual processing here. So maybe I'm only interested in the lines that in the talks that start at 9 a.m. And maybe I only want to print out the title and the room, but not everything else here. So how can I do that? Well, I'm just going to do some tokenization. So I need to think about the schema of my data. So I need to read things piece by piece. So I'm first going to read the ID. That is delimited by a comma. Next one is the time. Then I have the title. Oops. And finally, I have the room. And now I just add a condition here. So if time equals 0900 AM, then print, and I'm going to use printf here. So we're just going to say print as n, and I want to have room and title. Yep, compiled, and there we go. Right, so you can see I have the room and the title here. So nothing really special. But is this really how we would build a data processing system? And I would say no, because this is like really low-level code, and it's very specialized to the data schema I have, and it's specialized even to the particular query. So if I want to run a different query on the same data, then basically I have to implement a new program here, right? So I can't really reuse these things. But fortunately, we're in a modern programming language here, so we can add abstractions on top of this, right? So I don't have to write it this way, but I can add more functionality, right? So for example, I can add an abstraction that will actually read the data schema from the file, because I have it here in the first line. So I can say type schema is a vector of strings. And I can also add a class record. So records now have fields. Also add a type for fields. Type fields. We're just working with strings, so that's okay. Fields schema of type schema. And then maybe I want to have some by name lookup here in records. So in Scala, I can define an apply method, which takes a string, and this will give me back a string. And the way I'm going to do this is that I take the index of this name in the schema and use that to index into the fields array. So now I want to read my schema from the file. So I'll just say schema is in .next until new line. And then I'm going to say split this by commas and convert it to a vector. So we haven't gained that much at this point. But what I also want to do is I'm really not so happy with this while loop here, right? And this implementation detail that we're using, a specific scanner class, is kind of leaking into the abstraction. So I want to have something which is more like a function process CSV that will take a file name and invoke a callback with a record object. And now I'm just going to move this into this function here. And well, we also need to create the scanner here inside. And here we're passing the file name that we're given. We read the schema. And now we no longer know about what fields are in the file, because we want to be generic. So what are we going to do? We say we map over the schema, and for each element in the schema, we are going to call next. So, and then we are going to construct a record with the fields and the schema. And we're going to pass that to our callback. So there's one little problem here, because we're uniformly using a comma as a delimiter here. But for the last field, we actually need to use a new line. So we just insert in a conditional here. So if x is actually the last item in our schema, then it's going to be a new line, else it's going to be a comma. And then we can remove this while loop here and can just say process CSV source data talks.csv. And then we pass a closure, which is our callback, which will be invoked with a new record object. And here we can just say if record time equals 9 a.m., then printf record, and this becomes a string, and this one as well. So let's see if this actually compiles. Looks like there's one extra parent here. Okay, and name should be just a string, of course. I'm sorry? Ah, good catch. There we go. All right, that compiled. Let's see what we get. Yeah, we get the same thing, right? So this is much nicer now. So we have actual record objects which we can pass to another function if we want, and we can look up fields by name. So this adds a lot in terms of abstraction here, right? And we have basically factored out our input handling from the actual data processing, right? So that now there's a generic library function, process CSV, and this record class, and the application-specific code is much smaller now. But we actually want to do something more high level, right? So instead of writing this as Scala code, what we want to do is just say select room title from source data talks CSV where time is 9 a.m. So how are we going to do that? Well, it's actually not so tricky. So we just invoke a function parse SQL, which I have sneakily prepared on the side. And this function will give me an operator tree. So let's just see what we get here. We actually need to import this. So we are going to say this is an object engine extends SQL parser. Okay, and we also need to mix in simple query processor. There we go, and now we're getting something like this, which on first sight doesn't mean a lot. But let's look at the definition of parse SQL. So this is just using the Scala parser combinator library, and we have really defined the syntax of SQL statements here. So a SQL statement is a select clause and a from clause, a where clause, and maybe a group clause. And then we just go and define what these things mean. So select is a select token followed by either star or a list of fields. And the other clauses are defined in a similar way. So this part is not actually so interesting. But what is more interesting is what this parser produces. So what comes out of the parse SQL invocation is a query plan. And if you're familiar with relational algebra, this is really what is the core of all database systems. So a table is basically a relation, and every SQL statement can be expressed as a combination of one of these, of several of these query operators. So the most basic one is a scan operator, which just reads a table, and Then we have projections, which select only a subset of the columns in a table. We have filter, which selects only matching rows. And we have other operations like joins and group bys. So let's look again at our little code here. And let's simplify this SQL statement a bit. So I'm just going to remove I'm just going to do select star and remove the condition. Yep, compiling. And what we get is just a scan operator here. So what do we do now? Well, we have two pieces which do not quite together fit at the moment. So we have a SQL parser, and then we have our process CSV method. So there's something missing in between. And what we're going to do now is we're going to add a little interpreter for these relational algebra trees. So we're going to define a method which is called def_execop. It takes an operator and a callback. So this is from record to unit. And then we match on the operator. And right now we only have scan. So this is file name, and we can ignore the other parts here. And what we're going to do is we're just going to call process CSV with the file name and the callback. So let's see what happens if we do that. Exec ops, and then we obtain a record for each row here. Where's the, there we go. Thanks. Good catch. Okay. And of course we want to print out the record. Okay, so that has worked. So we actually print out our record objects, and as you can see, all of the records have both the fields and the schema, right? So of course this isn't quite what we want, so we're just going to add another method that prints just the fields here. So print fields, and I think I'm just going to copy this one here because I have it down there. There we go. Okay, print fields, and then we say print fields rec.fields. Compiling. Yep, there we go. Okay, so that was easy, right? So now let's do something a little more complicated. Let's add a projection. So let's say we are really interested only in room and title. Then this should compile, but we will probably get a match error. Exactly. So we get a match error because we're not handling all the cases here. So we're going to do project, and let's look at the definition of project again. We have an out schema, an in schema, and a parent operator. So what does that mean? So we're selecting the fields contained in schema from our parent operator, and we're renaming them to out schema. So let's go ahead and implement this. This is out in parent. So we're going to call execop on the parent. And then for each record we're receiving, we're going to select the in schema, and we're going to create a new record that has these fields and the out schema, and passing that on to our callback. So this doesn't quite work because we're using here a schema to look up fields in our record, but here we have only support for one field. So let's add another method that takes a schema and now returns fields. And this is just xmap this apply, which is exactly this method invocation here. So let's see if this worked. Recursive method needs result type. That's easy to fix. This is just unit. Okay, there we go. Yes, there we are. As you can see, we have, again, the room and the title, but all the other fields are gone. So now let's add filtering. So we want to have our where clause back. So we add another case in execop. Case filter. Let's check the definition. And now we have a predicate here and a parent operator. So again, we exec our parent operator, and we get a record, and we call a utility function. So if eval pred and record, then we invoke our callback with the record we got. And I'm just going to copy the definition of eval pred. There we go. So eval pred, right now we only support equality predicates because that's all we need. And each predicate has a reference, which can either be a field name or a literal value. Right? And the literal values are all a string, so what we get back here is also a string. And this is a Boolean, so we can match on it. Okay. There we go. So you can see it's a shorter list, and well, we can play with the statement a little, so we can actually select the time as well here. And you will see that, well, we have really selected only the ones that happen at 9 a.m. Right? So this is basically all that is needed to implement a very, very simple SQL processor here. We could do more. We could add joins. So in the all the code is also on the web. So here's a version that adds joins. A basic join is nothing else than a nested loop that looks for identical keys in both of the records. So this is a natural join, and that can be done by just iterating over the left parent and the right parent, and taking the intersection of the schema, and then seeing that okay, all the fields that occur in both records are actually the same, and only then invoking the callback here. Right? So this one is not very efficient. It has quadratic complexity. So what you really want to do is a hash join. And that works as follows. So you create a hash map, and then you iterate over the left parent, insert all the records you get into the hash map with their respective key, and then you iterate over the second table and look up the values from the first one in the hash table, right? So this one is much more efficient, in particular if the left table is much smaller than the right one here. Okay, so this works, and well, we can play with it and run some interesting queries here. But the big question now is, what about performance, right? Because well, we started with something that was very simple and very low level, and now we added all these abstractions here. So we added an interpreter, and well, everybody knows that interpreters are rather slow, right? And actually, we can run some benchmarks here. So I've downloaded a file from the Google Books Ngram viewer, which contains words that occur frequently in Google Books. And we can just check the size here. So this is a 1.7 gigabyte file. So it's not what you would call big data, but for running it on a laptop, it's already pretty substantial. So let's just see what's the performance here. So I'm just going to run a little statement here. So this is essentially just running the same interpreter, only that I have compiled it before. And we get some results. So we're just looking for a keyword here, but you can see it's taking quite a while. right? And so it has produced some output, but it's not done yet crunching all the data. And at the same time, we could actually look into, well, what would happen if we load this file into a MySQL database? And I did that earlier as well. And you can say that, well, on my laptop, this actually took a little short of 8 minutes. Right? And then actually running the query in MySQL, if you go to the bottom here, then you can see, well, this has taken almost a minute. OK, so our little interpreter is back here. So this is microseconds. So this is 38 seconds. Right? So it's faster than MySQL, but it's not really, really fast. And what I'm going to show next is, hoping we still have some time for that, that we can actually basically run the same kind of interpreter, but turn it into a compiler so that it will generate low-level code that does the query, similar to the one we started with. So if I select that version, which is called staged here, then, well, it also produces a result. But hopefully it should come back much faster with an answer. 1, 2, 3, 4. Yeah. Still taking a bit. So in any event, while it's running, let's see what's necessary here. And so our secret weapon here is basically going back to the literature on partial evaluation. So if anybody heard the term Futamura projections, then this is a concept that was invented by Yoshiko Futamura back in 1971. And the idea is that, well, whenever you have an interpreter, and if you can specialize this interpreter to a given program, then what you obtain is a compiler for that program, right? So there's a key sentence here. It is shown how a partial evaluation program can serve as a generalized compiler. This is done by partially evaluating an interpreter, which provides a semantic and syntactic definition of the language which is to be compiled. And in our case, we kind of have a secret weapon here in Scala. We have a framework which is called LMS, which is short for Lightweight Modular Staging. And the idea is basically that we use Scala as a glorified macro language to generate highly efficient Scala or C code. There's more stuff there, so there's an extensible IR and support for custom transformers and things like loop fusions. But in this case, we really rely only on the generation part, using Scala as a macrosystem. So let's look at the, so I wonder why this.
You ran it on stage before?
Yeah, I think this one should. Well, let's actually try the fastest version. So this one should be called C. And this one should be really quick. Yeah, you can see. So this one was just 3 seconds. And basically, all we need to do to turn our little interpreter into a compiler is we change the types. So the way LMS works is that we have a special type constructor, which is called rep of t. And well, whenever you have a normal Scala value, like int or string, then this will just be executed right away. But whenever we have a value of type rep of t, this signifies that we generate code for this expression. So if I have something like a rep of int plus a rep of int, then I will not perform an addition right away, but I will generate code to perform this addition. And in this case here, if we look at the staged version, basically the primary change we need to do is we need to change the type fields from vector of string to vector of rep of string. So what does that mean? That means that record actually becomes a mixed stage data structure. So fields are dynamic values because they depend on the actual data, whereas the schema is a static value. So there are no rep types hidden in the schema. And what that means is that while all the computations that just involve the schema are completely evaluated at code generation time. And similarly for the interpreter, all the operators are still static values, right? So the operators are basically the program that we're specializing on. And only in the callback, inside the record objects, there are rep of t values hidden for the fields. And then we can do more specialization, so we can actually add internal data structures like hash maps for joins, which are specialized to the particular schema, right? So right now our code was very generic, so we were only operating on strings. But here we can generate hash tables specialized for integers, for even byte values, or for particular kinds of strings. And let's just have a quick look at the code that is generated. So that would be this one here. So this is C code. Let's just take this one. Yeah, so this is basically, I think you can immediately recognize this looks pretty much exactly like what we started with, right? So we have removed all the interpreter overhead and are back to the beginning. Only that we still have all the productivity benefits in having a full SQL processor here. But we don't have to pay a price in performance. And we can either generate Scala, or we can generate C code here. And if we generate C code, we can actually play some more tricks. So we can even optimize the I/O level. So instead of having this scanner object, which is invoked all the time and needs to go through the file system API to load data, we can just memory map the input file here so that it becomes accessible as a byte buffer. And that means we completely eliminate the data copy. So if we have touched the input file before, then the operating system will take care of actually keeping it in memory, right? And this is why we were getting this fast execution for the C code here, right? So this is down from 38 seconds to just 3.7 seconds here. Right, so this is a lot of C code that is generated here, and but the input is still the same, right? So this is the C code generator. So here's our custom scanner implementation, and you can see that we're still using classes and methods and everything, right? So it's still high-level programming, only that we're making the operations explicit. So here we introduced this memmap call, actually, just providing a Scala method that will generate the corresponding C code at generation time. And here we're also using specialized data structures. So we're switching from just strings to an abstract class rfield, which has string and integer subclasses. And strings are actually represented as pointers into the memory buffer that corresponds to the memory mapped file here. Yeah. And all the rest, as you can see, is basically the same, right? So you have eval pred, eval ref, exec op. There's one method, result schema, which just computes the schema, and that is basically used in hash joins to make sure we have the right fields here before looking at actual records here. And then we have different data structure implementations, which are again, if we look at array buffers, for example, which are again specialized to the data types. And we actually, one thing that fits very nice with this mixed stage record abstraction is that we can very easily implement a column-oriented storage here. So what that means is that if we have a complicated query that only touches a subset of the fields, then we only need to access the memory inhabited by these fields. So we don't need to load big records into memory if we're only accessing a small number of fields here. Right, so you could say, well, this is just a toy, and does this really scale? So, well, of course, a real database does a lot more, but we actually implemented something which is a bit more substantial. So this is a joint project with the database group at EPFL and group at Oracle Labs. It's a system called LegoBase. It's an in-memory database query engine that compiles execution plans from the Oracle database to C code at runtime. And so this is a little bigger than what I showed. It's about like 3,000 to 4,000 lines of Scala code, but it supports all 22 queries of the TPCH benchmark. And the message here is that, well, it is indeed possible to write these high-performance systems in a high-level language by going the way of runtime code generation. Here are some experimental results. So we're comparing to a well-known commercial database system called DBX, and we can see that, well, we're getting very good speedups in most of the queries, so up to 20x. We're also comparing to another state-of-the-art query compiler, which is called Hyper, and we can see that we're also faster in all cases than that system. So this is work that was just recently presented at VLDB, and we actually received the Best Paper Award for this. So this brings me to the end of my talk. The message here is, well, my slogan, abstraction without regret, right? So we can have the cake and eat it too. We can have productivity and performance by having this stage distinction and using high-level abstractions at the generator level and then generate code which is specialized and low-level. If you want to know more, there's a website. There's a few tutorials and also some notes about what I presented here. Thank you very much. Are there any questions? Yes, please.
Are there any plans to include this sort of system into a commercial database like Oracle?
So right now, this is on the research level. I can't speak for Oracle about product strategy or something. Yes?
Would it be safe to say that the commercial database that you're comparing, which is very optimized code, but for generic operations, they then come back for a particular skill. And where what you are doing is that I'm giving it an SQL and it's only generating code. It's not doing anything generic. It's only generating code for the specific operation this particular query needs. And because of that, it's the speed up is we're getting.
Yeah, so that's a very interesting question. So one reason why these existing database systems have such big code bases is that there is actually a lot of manual specialization, right? So we actually looked at the Postgres code and counted, I think, 7 implementations of B trees and memory page abstractions. And this is all done for performance, right? But in a generic system, you can only go so far with specialization, right? You're already at 10 million lines of code. So if you want to go all the way, then, I mean, it just isn't manageable anymore, right? Whereas here, we're generating code that is specialized to a particular query. So we don't have like 5 different specialized hash table implementations we can pick from, but we're generating a specialized hash table for a given query and for the given schema that is used in that query, really. Yes, please.
Yeah. So are there cases like for range queries
Mm-hmm.
that I think typically use indices? Are there cases like that where you know, are maybe, is it always a win to use the compilation strategy, or are there cases where you think?
So I think compilation strategy is always a win. Because, I mean, anything you can interpret, you can also compile and run something faster. So the only question where you might be better off running an interpreter is if you, if sort of compilation time takes more than query execution time. But in that case, I mean, you don't need to worry about optimization at all, right? If the query doesn't take a long time, then why bother? Okay, who was first? I think over there. Yes. So a couple of things. So inlining is basically driven by the types, right? So whenever I have a Scala function that just goes from rep of A to rep of B, then it's still a Scala function, right? So any function call will be unfolded or inlined during the generation stage, right? So if I want to have a function in the generated code, I need to be explicit about it, and I need to invoke a fundef or lambda constructor that will actually produce a function of type rep of A to B, right? Which I can then call in the generated code. But this is actually an interesting question. I mean, you don't always want to inline because that will also blow up your code size, and you will have iCache problems in some cases. But you can abstract over these choices, right? So you can have a constructor that takes a Boolean parameter and will either inline or not inline the function, depending on context or whatever. So we don't try to make automatic inlining decisions, really, because that is very hard in general, and compilers mostly get it wrong. But we really want to put the programmer in control here, right? So the developer of the database system. Okay. So I think we are running out of time, so please feel free to grab me during the break if you have any more questions. Thank you.